right, so let's talk about intermolecular forces and some of the trends of physical properties that we see in chemical samples. So, just kind of to recap, when you inspect a substance and determine what intermolecular forces are present, we've already talked about as we see an increase in intermolecular forces present in a sample, we typically see an increase in the temperature in which that sample boils. So, if the basis of that relationship is that the more intermolecular forces present in that sample, the more attractions that that sample has to hold those molecules together. So there's more attractions holding those molecules together. So that's why it takes more kinetic energy to get that sample into the gas phase. You'll see a higher boiling point temperature. So some of the physical properties that we're going to talk about, viscosity, surface tension, and vapor pressure, all use that same type of logic that the more intermolecular forces present in the sample, the more attractions that that sample has. So it kind of makes sense when we think about viscosity or the resistance of a liquid to flow. So, for example, honey or molasses, those are very viscous substances because they flow very slowly. There's lots of resistance there for that substance to flow. So what we see in terms of intermolecular forces is that as there's an increase of intermolecular forces present in a sample, your viscosity increases. But again, if we think about intermolecular forces as attractions for molecules to one another, that kind of makes sense. Those molecules are very attracted to one another, so just allowing them to flow past one another will be quite difficult. So you'll see that that sample flows very slowly. And so what you'll see is as intermolecular forces decreases, if there's not as much attractions in your sample, you'll see lower viscosities. So the substance will behave more like water and flow very rapidly. Something else with regards to viscosity, and I think we kind of experience this as well, as you increase the temperature of your sample, your viscosity will lower. So that kind of makes sense, if you have honey in a jar or in a bottle and it's very difficult to squeeze it out to get it to wherever you want to go to put that honey for like some recipe or something. Oftentimes what I'll do is just pop it in the microwave for like 15 seconds to warm it up. I'll warm up that honey or warm up that molasses in order to get that substance to flow out of the container more easily. So the trends that we see here is as intermolecular forces increase, we see an increase of viscosity. And remember, the more viscous the substance, the harder it is to flow, it behaves more like honey. But something else we also see is as we increase the temperature of our sample, we'll see a decrease in viscosity. So yeah, if you just think about honey, then I think you can understand this trend. So here's some viscosities of different hydrocarbons. So remember, these are nonpolar substances. Nonpolar. So the only intermolecular force present in these hydrocarbons are London dispersion forces. So I have a series of hydrocarbons where the chain length, the number of carbons increases. So as we go down this table, our molecular mass or molar mass of the substances increases going down. And so since molar mass increases, we should see an increase of intermolecular forces as we go down this table because London dispersion forces are increasing as we increase our chain length. And what you see here, as our intermolecular forces increase, molar mass increases within this table, our viscosities increase. So that goes along with our trend. All right, so that is viscosity. Again, if you just think about intermolecular forces are attractions of molecules to one another. So the more attractions, the harder it is to move those molecules past one another in terms of flow, and how we measure that is in terms of viscosity. All right, so another physical property that we can relate to intermolecular forces is surface tension. Just straight definition of surface tension is the net downward force experienced by molecules at the surface of a liquid. So where we observe surface tension of a sample is always at the surface of a liquid. So at the surface, there are no molecules above that sample. The bulk of the sample is below the surface. And so since there's fewer molecules at the surface of of the sample, essentially there's more of a downward force of attractions if there's a lot of intermolecular forces present. So that net downward attraction of intermolecular forces going down, if you kind of think of them as vectors, there's no counterpart molecules up here for intermolecular forces to push the sample up. So that is the basis of how surface tension comes about. It's based upon intermolecular forces of the bulk of your sample, that there's a net downward force at the surface because there are no molecules above the surface. And so with liquids, they will try to minimize their surface area, and that is a consequence of intermolecular forces. And this is often why liquids will form spherical droplets if you put one drop of it on a surface or something. And so a sphere will give you the smallest possible surface area. And we talked about this with London dispersion forces, that the more cramped you put your sample, you minimize the surface area there. And so how this trend manifests itself in terms of intermolecular forces, the more intermolecular forces present in your sample, then there's more of a downward force of net intermolecular forces at the surface of the sample. And so what you'll see are with samples with high intermolecular forces, you will see high surface tensions. So something like water. We know water has a lot of intermolecular forces present. It has London, it has dipole-dipole because water is polar, and it has hydrogen bonding. So water does have a lot of surface tension. And then this figure kind of shows where that net downward force happens at the surface. So you can see here, like in the bulk of our sample here, there's if we think about this molecule in the middle, we'll focus on that middle molecule. There's attractions from this center molecule to the one over here, over here, over here, over here, over here. So it kind of, all those net force attractions kind of cancel one another out. So this molecule doesn't feel like it has to move in any one direction because it's being attracted from all sides of it, because that molecule is surrounded by identical molecules all around it. But what's different at the surface is that at the surface we're missing some molecules above at the surface. So there are no attractions pulling that molecule up to cancel out the rest of those intermolecular force attractions. So there's this net downward force, which is what surface tension is, based upon our definition. So the last trend that we will talk about in terms of intermolecular forces and physical properties is vapor pressure. So oftentimes we symbolize vapor pressure as P because it's pressure, and we put vape to mean vapor pressure. So you might have never heard of this term, but we've all experienced vapor pressure. So the definition here is just vapor pressure is the vapor in dynamic equilibrium. You'll talk about equilibrium in 1220 with a liquid sample. So it's an equilibrium between vapor, so a gas, and a liquid. So all liquids have some amount of vapor above the liquid surface. So this might be a concept that sounds new to you, but we've all actually experienced this in real life. So if you've ever used nail polish remover, which is acetone, it's the chemical acetone. Nail polish remover, you buy it from the store, it's a liquid. But if you ever pour some acetone out, it has a very distinctive smell. So that smell that you are experiencing is actually the vapor pressure exerted by that liquid. So I think by our own experiences, we know some specific liquids that have certain smells. So those samples smell a certain way because sometimes we say, oh, they're volatile liquids. That typically just means that those liquids exert high vapor pressures at, ambient temperatures, whatever temperature you're at. So all liquids exert some type of vapor pressure at our normal temperature and pressure. So other examples of things with high vapor pressures that you experience through smelling them, acetic acid. So like vinegar, so like white vinegar has a very distinctive smell because acetic acid exerts a high vapor pressure. I already said acetone. If you haven't used nail polish remover, you can also think of like rubbing alcohol. Rubbing alcohol is mainly isopropyl alcohol, so it's an alcohol And so that substance also exerts a high vapor pressure. And I think most of us know that rubbing alcohol has a very distinctive smell. And what you're smelling is the vapor pressure being exerted by that substance. So, why do some liquids or some samples have high vapor pressures and others don't? It has to do with intermolecular forces and the temperature at which that sample is at. So, I mentioned that we smell these things at our ambient temperature and pressure. Because at any temperature, some molecules in a liquid have enough energy to overcome intermolecular forces and break free into the vapor phase. So that's why you can smell the acetic acid in vinegar, because at room temperature, there's enough kinetic energy to allow some of those acetic acid molecules to escape into the air so we can smell it. And so, as you increase temperatures of that sample, you will allow more molecules to break free into the vapor phase. Not so much that it's boiling yet, but enough that you can smell it. So, if you've ever boiled vinegar before, like on the stove, or just heated it up to maybe like dissolve some sugar to make some pickles or something, heat up that vinegar to allow more sugar to dissolve, you'll notice in your kitchen that your kitchen will just reek of vinegar because you're allowing more molecules of that acetic acid to fill up your room into the vapor phase so you can smell it. So heating up vinegar will allow more of those smelly acetic acids into your space. And so that's what you kind of see in this graph. At a lower temperature, let's say at this temperature, so down here, this is kinetic energy. So essentially temperature. So this graph is essentially a Boltzmann distribution of molecules at any given temperature, and we've talked about this in chapter 9 about gases. So essentially what this is saying, at this particular minimum kinetic energy, particles will escape to the gas phase. So at a lower temperature, we can see this blue area under the curve. Only a small fraction of molecules have enough energy to enter the gas phase. But as you increase the temperature, you change your Boltzmann distribution a little bit, and so you get a larger tail region, which we see here. So we see at higher temperatures, as you heat up your vinegar, that more molecules will escape into the gas phase, essentially increasing your vapor pressure of your sample, so then it fills up your kitchen and it smells really bad. All right. So in an open vessel, eventually a liquid will almost always completely evaporate. So we've also experienced this. The note here is in an open vessel. So if you leave a glass of water out for many days, eventually it will completely evaporate. And that's because water has a vapor pressure and those water molecules will slowly enter the liquid to gas phase. Although slowly, it's not boiling, but it will enter the gas phase because of that vapor pressure, and eventually all of the liquid sample, will disappear. And so we also saw this in lab, where we combusted heptane in our chemical reactions lab. And sometimes, you put a couple drops of heptane on your watch glass and burn it. But if you weren't fast enough in lighting your heptane, sometimes all of it would evaporate before you could even light it. And that's due to the vapor pressure of heptane, that it all evaporates before before you can actually light it on fire. Or we know that acetone and rubbing alcohol, they evaporate quite rapidly compared to water, and that has to do with intermolecular forces. So that's in an open vessel. Most substances will eventually evaporate. But we have a different situation in a closed container. So in closed containers, we can then measure our vapor pressure of our system because that liquid and gas are in equilibrium. So in this photo, or in this diagram, what we see is we have this evacuated flask with zero pressure, and then we insert some liquid ethanol into the system. And so what we see, once that ethanol enters that vacuum, some of the gas particles leave the liquid state. And if we close up that vacuum, then we can measure the vapor pressure, so how many gaseous ethanol molecules are in the gas phase versus how many liquid molecules are in that phase as well. So what you'll see in this third picture is that you have both ethanol molecules in the gas phase and the liquid phase at the same time. So I mentioned that equilibrium in the definition when talking about vapor pressure is a dynamic equilibrium. So what that means is that the net amount of gas particles and liquid particles do not change. But what's actually happening is that liquid molecules are entering the gas phase in one direction, but also gas particles are entering the liquid phase at the same rate. So essentially, you have gas or liquid going to gas and gas going to liquid, both at the same rate. And so you don't see any net change in amount of liquid or gas. So that is what a dynamic equilibrium is. And so when we measure how much pressure is exerted by that liquid, what is that pressure of those gas particles? That is how we measure vapor pressure. It's that equilibrium pressure of vapor above a liquid. So this vapor pressure that we measure in this type of experiment that we do is dependent on some things. I mentioned that this vapor pressure that we measure is dependent on the temperature of your sample. So vapor pressure does depend on a few things. So, I mean, we're talking about intermolecular forces in this chapter. So, obviously, vapor pressure depends on intermolecular forces and temperature, like I said. So, if we're looking at that third picture in that previous diagram here, and so the gas particles that are above the liquid in this experiment, that's our vapor pressure. So if we increase the temperature of this whole sample, we're giving that liquid more energy. And so if we energize those molecules, more gas particles will enter, or more molecules will enter the gas phase. So typically, one of the trends that we see is that as we increase temperature of our sample, we'll have a higher vapor pressure. And again, the same kind of concept, if you heat up vinegar, you will smell more of that vinegar distinctive smell because we're increasing the temperature. We're sending more gaseous acetic acid molecules into the air, so we smell it more. Also, intermolecular forces will affect the vapor pressure of different samples. So typically what you see is that the stronger the intermolecular forces present in your sample, the lower the vapor pressure that you will measure. And again, if you remember, intermolecular forces are just attractions of molecules, then that kind of makes sense. The more attractions that a molecule or sample exerts on its molecules, the harder it is to send liquid molecules into the gaseous phase. That liquid is going to hold on to those molecules more tightly, and so you will measure a lower vapor pressure. All right, and so what vapor pressure does not depend on, these are important things, is the amount of liquid inside your closed container. So regardless of, whether you have, a couple milliliters of water in a closed vessel, or if you have, 10 liters of water in a closed vessel, if you measure the headspace on above the liquid and you measure the pressure of gases above that liquid, it should be the same number. So whether you have a container that, has a tiny bit of liquid, or if you have a really big container with a ton of liquid, if we measure the vapor pressure, as long as it's the same sample at the same temperature, evape, both those values will be the same, as long as it's the same sample and the same temperature. And then finally, kind of also based upon that, is the size of the container. It doesn't matter what the size of the container is either. You will measure the same vapor pressure above both samples as long as they're in a closed container with the same liquid at the same temperature. So let's expand on this first general trend. The higher the temperature, the higher the vapor pressure. So we know as we heat up a sample, eventually it will boil. So kind of like our vinegar example. You heat up your vinegar sample, you're sending more acetic acid molecules from the liquid phase to the gas phase, so we smell it more. But as you continue heating up that sample, eventually it will boil. So how does boiling relate to vapor pressure? So every substance, whether it's vinegar, water, whatever, has its own vapor pressure curve that relates the relationship between the vapor pressure, or the pressure of gas above the liquid surface, and temperature. So when a liquid boils, this is an important thing. When a liquid boils, the vapor pressure above that liquid is equal to the external pressure on its surface. So on Earth, what is the external pressure? Well, that is 1 atmosphere. So when something boils on Earth, like if it's on your stovetop, when that sample boils, the vapor pressure of your sample is equal to 1 atmosphere, and then that is the temperature. At that point where your vapor pressure of your sample is equal to 1 atmosphere is your boiling point temperature. So that's why we often say the normal boiling points of liquid is the temperature at which the vapor pressure above that sample is equal to 760 torr, or 1 atmosphere. So on Earth, that is a pressure of 1 atmosphere. So that's true for any substance. So whether we're talking about ether, or if we're talking about ethanol or water, if we look at those specific relationships between vapor pressure and temperature, we see that they kind of look different. They have different steepnesses to it. And all of them achieve 760 torr, that vapor pressure, P vape, equals 1 atmosphere at different temperatures. So here you see for ether, in order for diethyl ether to achieve 760 torr of vapor pressure, it requires a temperature about 35 degrees Celsius. So what that means is that the boiling point of ether on Earth, so that's why we say normal boiling point, is 34, or about 35 degrees Celsius is the boiling point of ether. Or for water, the point at which water exerts a vapor pressure of 1 atmosphere is 100 degrees Celsius. And so, just kind of to relate it to real life things, if you've ever used a pressure cooker at your home or in your life in some point, you know that doing pressure cooking cooks foods faster. And the reasoning is with a pressure cooker, you're cooking in a closed container where you can achieve a higher pressure. And so if you're boiling water at a higher pressure, not at 1 atm, maybe about like 1 and some change atmospheres instead, what you're able to do, so let's say here, if you're able to achieve a pressure of, over 800 torr, what you're able to do is increase the boiling point temperature of water, but you have to do it in a pressure cooker, something that can achieve a higher pressure. And so you're cooking at a higher temperature with a pressure cooker device. Or conversely, if you've ever read the back of a package of how to cook something like noodles or something, and it says boil for 8 minutes until al dente, but sometimes they'll put like a little note saying at higher elevations cook for 12 minutes or something. And so the reasoning there is at higher elevations, your ambient pressure is lower because you have less gas particles above your head. So that's often why people say, or, like the NFL trains in Denver, Mile High City, because there's less air pressure up there. And so they can train under more strict conditions. And so when they go to like regular atmosphere, that they can train better or like perform better. So essentially there's less air in Denver, less pressure in Denver, and so since there's less pressure, water will not boil at exactly 100 degrees Celsius. It'll actually boil a little bit lower, and so you have to cook your noodles longer. All right. So let's keep expanding on this vapor pressure and temperature relationship. So it's not quite a linear relationship. So as you see, all these curves, or all these temperature pressure relationships are not straight lines, they're curves. So this relationship, this curve that you see between temperature and vapor pressure, it's not linear, it's actually a logarithmic relationship. And so we can actually graph this relationship and determine the vapor pressure of any substance at a given temperature using the Clausius-Clapeyron equation. And that's what this equation is right here, where the natural log, so it's logarithmic, it's actually a natural log of the vapor pressure, so this is P vape, is related to its temperature and its enthalpy of vaporization. So essentially the energy required to make a molecule go from the liquid phase to the gaseous phase. So here's the equation where the natural log of your vapor pressure is equal to negative your enthalpy of vaporization, which is it's a literature value, it's a constant, divided by RT plus C, which is a constant. So temperature here has to be in Kelvin, as all stuff that we've been doing, it needs to be in the unit of Kelvin. And R is not our gas law constant that we used in chapter 9. It's not 0.08206. It's actually our 8.314 joule mole Kelvin value. That is our R value. And the reasoning is because our enthalpy, like all enthalpy values, has a unit of, typically we report it in kilojoules per mole, but if you use it within this equation, it must be in the unit of joules per mole. So you can see how those units cancel out with one another. You need to use this R constant, which is still the gas law constant, it's just in a different unit, in order to get our delta H value to be in joules per mole. So this slide explains exactly what I said before, going through each of the different variables here in our Clausius-Clapeyron equation. So you may be asking yourself, well, why do we have to put the natural log portion there in front of vapor pressure? The reasoning we do this is because if we do natural log of pressure and do, negative delta H over RT plus C, putting all of that vapor pressure and temperature information in this form actually gives us a straight line where ln of pressure equals y. This portion of our equation equals m, so the multiplication in front of x. So then x becomes 1 over t plus c. So this, putting it in this form, makes the Clausius-Clapeyron equation be a straight line, essentially turning this curved line into a straight line, which I'll show you on the next slide here. And then here tells us all of the different variables within our Clausius-Clapeyron equation. And I'll mention enthalpy of vaporization must be in the unit of joules per mole in order to work out into this equation. Or if you're given pressure and temperature information and you have to back calculate to figure out what delta H of vape is, when you calculate that value, it will have the unit of joules per mole. So if the question asks for that value in kilojoules per mole, you'll have to do a little bit of manipulation. And so straight lines are much easier to work with than curved lines like we saw previously. So when looking at vapor pressure temperature information for a sample, putting it, essentially graphing natural log of vapor pressure versus 1 over temperature. It's 1 over temperature because temperature here is in the denominator. If you graph this, where ln vapor pressure is on your y-axis and 1 over temperature is your x-axis, you get a straight line. And that's really great because with straight lines, you can get a slope. Right? We can do our rise over run and get our slope. So you will do this in 1220. You'll do an experiment where you look at the vapor pressure of a sample at different pressures, and then you can go ahead and calculate your delta H of vaporization for an unknown liquid. So if you use Excel and graph natural log of vapor pressure versus 1 over temperature, calculate your slope from your graph, you'll get, if you inspect your Clausius-Clapeyron equation, you know that m is your slope. That's your m. So you'll get some type of equation, y equals mx plus b. But because we said y is ln of vapor pressure and x is 1 over t, our m value here is our slope. And so you can calculate what your vapor pressure of your sample is. Depending on what your slope is, you just have to multiply your slope by our R value, the correct one, and take the negative of it. And you can calculate the enthalpy of vaporization of an unknown liquid. So that is the Clausius-Clapeyron equation. We can also, so this is how you calculate vapor pressure with many graphically. So we have many different data points here. We can also determine, oh yeah, so that's what that is. And you'll do this in 1220 in lab. You can also apply the Clausius-Clapeyron equation non-graphically, as long as we know 2 different data points. So we need a pressure, a vapor pressure of like 1 at 1 temperature, 1 at, I'll say at temperature, let's say A, and then we have to know a different vapor pressure at temperature B, or 1 and 2, whatever, 1 and 2. So we can also use the Clausius-Clapeyron equation, but we need to know 2 points. And the reasoning there is because any 2 points on this graph will always make a straight line. And so we can use a different equation. It's still the Clausius-Clapeyron equation, just kind of shown a little bit differently with some mathematics rearranged in it. So we can get a different Clausius-Clapeyron equation that compares 2 different data points. So you can see how this kind of looks similar to the previous one where we looked at the Clausius-Clapeyron equation as a y equals mx plus b as a line, but we can also say through mathematical manipulation that the natural log of the ratio between the vapor pressure at temperature 2 over the vapor pressure at temperature 1 equals the enthalpy of vaporization over R times 1 over T1 minus 1 over T2. Or you can also write, because of the rules with logarithms and temperature, or 1 over, inverse functions, you can also say natural log of pressure 2 over pressure 1 equals negative delta HVAP over R 1 over T2 minus 1 over T1. Regardless, these are both the same equation. The reason I kind of give both of these is because, as you notice here, we put pressure 2 over pressure 1. And then when we do this difference in temperature, we do 1 over T1 minus 1 over T2. So see how we kind of lost that negative sign, but we do 2 over 1 and then 1 minus 2. So I feel like sometimes that confuses students, and you have these changes in condition 1 versus condition 2. But you can also write it in this way where we do natural log of 2 over 1 equals negative delta H vape over R 1 over T2 minus 1 over T1. So we do 2 over 1, 2 minus 1. So we kind of keep that same consistency. We do 2 and then 1, 2 then 1. All right, so that goes over the Clausius-Clapeyron equation. There's many different practice problems given in the Chapter 10 handout where you calculate the delta H of vaporization for a substance given 2 different vapor pressure measurements at 2 different temperatures. And we will go into how we get enthalpy of vaporization in the next lecture video when we talk about phase changes.